Yeah. Okay, so when we're doing stuff in polar, again, the idea is, keeping the really simplest terms, I'm trying to do something like this, which would be insane to do in rectangular, right? My limits of integration would be all over the map. So the idea of polar in general is I split this up into a bunch of sectors. Remember, in rectangular, we split it up into a bunch of rectangles. Here we split it up into a bunch of sectors, and that allows us. So, you know, the Reader's Digest version would be, and I want to remind people, there's a picture that I draw in every calculus class, and those who've been in my previous classes, you've seen this many times, but it is one of the most important facts from geometry that we use in calculus. And this might be the single most important thing from geometry that we use because we use it so often, and that is the relationship between everything. If that's the center of the circle, then this is called the central angle. This is my radius, this is the area of the circle, this is the length of that portion. The pie-shaped wedge, what is that shape actually called? I know most of you know this.
A sector.
It's called a sector. So when you hear the term sector, that's what a pie-shaped wedge is, but it actually has to come from the center. It's not random. I don't just do it anywhere, because there's no rules or relationships if it were random. So there's a simple set of equal ratios that, if I know, helps me derive other formulas. And a lot of your Calc 1 formulas at the end of the course, arc length, surface area, things like that, some of them come from this. And that is, theta is to the angle all the way around, as the area is to the area of the entire circle, as the arc length is to the arc length all the way around, which of course would be the circumference. These three are always equal, and if I put any two of them together, that's what's called a proportion. That math vocabulary. A ratio is a quotient. A proportion is any two ratios that are set equal. That's the term, that's where the word proportion comes from.
You put a plus instead of an equals.
I'm sorry?
You put a plus instead
Oh, they use that. I'm in a very positive mood today, that's why I'm adding them. So, any two of these put together gives us a simple formula. So for example, if I put these two together, then that means that area equals theta over 2 pi times pi r squared, which gives us 1/2 r squared theta. That is an astronomically important relationship, that the area of the sector is 1/2 r squared theta. And that's part of what we used to be able to do the polar coordinates. You go, oh yeah, okay. Now, in Calc 2, r was always a function of theta because I can only do the problem with one independent variable. So when I wanted to do this, and let's say that angle is theta 1 and that angle, let's say, is theta 2, then I set up the integral from theta 1 to theta 2 of 1/2 r of theta squared d theta. That's hopefully what you learned in Calc 2. That's one of, my goodness, and certainly other than series, that may be one of the most important things. And in terms of integration, that's the only integration technique probably you're actually going to use in Calc 3. You don't, how many integration by parts have you done? None. How many are you going to do? Probably none. Partial fraction decomposition, you're not going to do any in this course. Trig subs, none. Miscellaneous substitutions, none. Evil trig, none. You're going to do those later. You're not using any of those in this class, but you are going to do polar integrals in this class, and that's what we got. This is the Calc 2. Cool. And depending on the problem, this might be easy. So now in Calc 3, where we made r and theta independent variables, then I go backwards one step, and I do the double integral over, I'm going to call it the region in the r theta world, rather than the xy. Except in special cases, theta is always going to have constant limits. Because you're not switching unless it's circular in some nature. So theta is going to be constant. R isn't going to be constant in general. R is still going to be, I'm going to go r as a function of theta. But now what is my integrand? It's, if my original function was whatever it is, this is going to become f of r theta. So I had an x squared plus y squared, now it's an r squared. I had an x plus y, now it's an r cos theta plus r sine theta. This is where I switch the x's and y's, and then I get what? R dr d theta. Okay, I remind people that that's what you got. Why? Because when my integrand is a 1, and I'm actually just doing this problem as a double integral, Remember, you don't set up double integrals to do what you can do as a single integral. We know that. But if I had done this problem as a double integral, then my first integration would be 1/2 r squared d theta, wouldn't it? It'd be back to here. That's how you know, oh, that's why I need that r. Okay? That extra term has to be there. Forgetting the r is a death nail. It won't, no matter what I write, I won't get a correct thing. So what I want to do today is say, how do we do a three-dimensional problem where polar makes perfect sense? But what kind of shape would I have to do polar in 3D? Anybody want to guess? Circular cylinder. If you got a circular cylinder, then the XY plane, I still have circular stuff, but Z is Z. So we have a new thing. We're going to do the three-dimensional analogy of polar coordinates, and they're called cylindrical coordinates. You're going to like this. In cylindrical coordinates, x becomes r cos theta. Y becomes r sine theta. And z stays z. Should I do that again? Yeah, people love cylindrical coordinates because you don't do anything with the z. Z stays z. Because I'm only going to do this if it's literally cylindrical in nature. Okay? Now, could I have done it for that paraboloid a moment ago? Sure. But I would keep z as z. There'd be no advantage to changing z. That's the second half of today's class. Those are uglier problems. So in cylindrical coordinates, it's basically polar coordinates in 3D. That's it. It's actually that simple, and it's very, very common because in three-dimensional situation, okay, I don't want to do a rectangular integration if I've got circular regions. It's too hard most of the time. So the key is, how do I change the integration? Well, the nice thing is, it's going to be a dz dr d theta, but I still throw in the extra r. That still goes in there because I need that for the xy plane part. So we're going to do, by the way, in the fall, this lecture generally occurs within a week or two of Thanksgiving, just so you know. So I always bring up, because I know it's only July, and it's early enough that I can talk about food because you guys hopefully aren't that hungry. But, you know, in my house, Thanksgiving is epic. But my wife makes a stuffing that you could eat. That's all you could eat. It is great. We do the most incredible turkey. But one of my favorite things is she makes cranberry sauce, where she actually uses the Cuisinart, grinds things, uses real stuff. But unfortunately, the rest of the world uses that nasty stuff that comes out of a can that when you open the can, it's still a solid, jiggly shape. You guys know what I'm talking about? Yeah. So our goal today is we want to find what is the center of mass of the nasty can of cranberries, because that actually is a calculus problem. That is the problem of the day. Like I said, in the fall when I do this, it's usually very close to Thanksgiving, so people, you know, they want to know, because they want to balance those cans of nasty cranberry sauce. Now, one of the things you notice when you open the nasty can, sorry, I shouldn't be picking on it, but I would never eat that. But then again, I don't eat Jell-O either, especially when it has the nasty fruit cocktail. You know, you guys know what I'm talking about? All sitting at the bottom. Wow, why people think that's a good thing, I never understood. So when you open that can of cranberry sauce, what do you notice? The top is kind of liquidy, isn't it? Tell me about the bottom of the can. It's much more dense, isn't it? Now, that's gravity. The density tends to increase as I go down, which means density generally is inversely proportional to height, okay, loosely. So what we want to do is we're going to take a can of cranberries, and let's decide, let's say the can is, I don't know, how big is a can typically about? Let's say 6 centimeters, maybe? And probably about 15 centimeters this way? I'm guessing. And that's probably reasonable. I've got this can that's about this size. And we're going to say that the density, I'm going to just say is loosely proportional to 1 over the height. that symbol in this context actually means proportion. We'll come up with something specific. Now, you're in real life. So, you know, Christian's looking around rapidly for the XYZ axes because he's got to put the can down and oh my gosh, there are none. I'm giving you a can. So guess what? You get to put them anywhere you want. So Zachary, where do you want to put your axes?
Down the center of the.
Well, okay, be more specific. You can't put them all down the center. What do you want to go down the center?
The axis.
Okay, so Zachary says he wants Z to go this way. I like that idea. You guys all like that idea? Center the can on Z. Now, where do you want your XY plane? Top, middle, bottom, random, way below the bottom. How about if we make... So I set the can on the XY plane. Does that seem reasonable to you? That's probably the most logical from a calculation setup point of view, because then I can start things at 0. Is this an absolute rule? No. This is what you decide. You can do whatever you want. You could say, I want to put the axis in the middle, or the plane in the middle. The problem with putting plane in the middle mathematically is now you're going to have negative values of Z, and when you're trying to do the density, and you can see potential issues can occur. So I said the density was loosely proportional to the height. So in this case, let's say then the density, which is a function of x, y, and z, by the way. Density always has to be a function of all 3 variables. To be a function of 3 variables, do you have to use all 3 variables? No, it just means you're having 3-dimensional input. Let's say that this is 1 over z plus 1. Why don't I say 1 over z? Because I said it's loosely proportional to the reciprocal of the height. Why not just 1 over z then? We'd have a problem at the bottom, wouldn't we? Yeah, it'd be infinitely dense, although if you've ever looked at those cranberries, they're pretty dense at the bottom, but they're not infinitely dense, right? So we'll put a plus 1 on the bottom so we don't get 1 over 0 at some point. So this is still loosely proportional. All right, so we got everything we need. This is the shape of the can. This is the density I would like to find the center of mass. That's it. So we're going to use yesterday's stuff and the new stuff we're about to learn, meaning how to integrate in cylindrical coordinates. All right, so now again, a reminder in polar in general. If you have a circle centered at the origin, and circles do not have to be centered at the origin. Sometimes they're centered elsewhere, and they're a little trickier to find when they're centered elsewhere. There's no question, okay? They're harder to work with when they're not centered at the origin, but when they're centered at the origin, life is good. Life is easy. So I have a circle that's centered at the origin. And the radius is A. So therefore, how do I convert this to polar? This I want to be as automatic as anything you do in this course. I don't even want you to have to think about it. Well, wouldn't that be r squared? And if r represents radius, radius cannot be negative, period. Some of you, when you were setting up your limits of integration, you had r with negative limits. That's impossible. You're in an imaginary realm at that point. No, r has to be a non-negative number because r represents the radius of a circle. So this circle here in polar is r equal a. That's it. Oh, so if I go a units from r and now I allow my theta to go from 0 to 2 pi, that's how I carve out my circle. That's one of the friendliest transformations there is. Another way to think about this is if I'm coming from the center and I take an arbitrary wedge here, an arbitrary sector, the radius is going to go from 0 to the outer radius. It's going to go from 0 to r. Okay, that makes it much easier. And my theta, all the way around. When the circle is centered at the origin, theta and r are generally really, really simple. But I want to give you an alternate view of something. What if? Okay, what if I said I've got r equals, let's keep it simple, r equals cos theta. No. Less friendly, but still not terribly complicated. Now, I don't know if I did this on the video, but I can't convert, I mean, r would be the square root of something, but I can't convert the cosine theta into xy. That won't work. I know that x equals r cosine theta, y equals r sine theta, and I know x squared plus y squared equals r squared. Boy, it'd be a lot better if each of these had an extra r, wouldn't it? Can you arbitrarily multiply both sides by r? Zachary?
If r is already able to be equal to 0, yes.
Yes. This is an absolute unbending rule that most people completely ignore, and it can have a huge effect. One of the things you learned as babies in math, you can never multiply or divide by something that can equal 0. Because if you have an equation, you multiply both sides by 0, now you have 0 equals 0, and you've lost your solution. If you divide by 0, that may be even worse. We can't do that mathematically, okay? But I can always multiply both sides by a variable expression if that quantity being 0 was already part of this. Is there a theta out there where r equals 0?
Yeah.
Yes. Theta is pi over 2, that would work. So I can legally multiply both sides by r. What if I had this? Could I multiply both sides by r? No. In fact, if I did, now I got this happy polar equation, it would be representing a different problem completely. I've gone to an alternate universe. Any result I get would be meaningless because it's no longer the same problem. That's why you have to understand there are certain restrictions. In this case, though, life is good. Because there is a theta out there where r would already be 0, multiplying both sides by r will not introduce anything that isn't already there. So multiplying both sides by r gives me this. So now my left side is x squared plus y squared. My right side is x. How about if I do x squared minus x plus y squared equals 0? How about if I make that, what goes here? Completing the square. Half the coefficient would be, and what goes here? The square of that. So this is a circle, if it helps you think of it like this. This is that's what this is. This is the circle of radius 1/2, centered at 1/2 comma 0. How do I know? Because I'm now looking at this. But here's the other thing. Okay, the circle's not centered at 0, but it's still a circle. Are we happy that it's a circle? Yes. But if I wanted to find the area using integration, is it 0 to 2 pi? Okay. I wonder how many things I'm going to have to merge later on today. As long as we don't lose anything. I love it that it told us. God, that scared me. I recharged that yesterday, so I knew it was absolutely full. Wowzers. All right. So I have an integrand with x, y's, and z's. Before, what did we do with our integrand? We changed the x's and y's to r sines, r cosines, and did our thing for polar. Now you're going to have an integrand with x, y's, and z's, and for me to switch it, this is the transformation I'm going to do. Okay? But when I did the r theta thing, remember we needed the extra r? And I showed you in the videos where that comes from. It comes from geometric thing. We don't just say it's an r. I showed the geometry, the area of the wedge. You got that additional r. So what do we do in this context? Well, it's really similar. So I'm going to draw a picture. This picture is in most calc books, but it's really hard to interpret because it's like that one. It's a picture of 3D. Okay? I don't need you to be able to reproduce the derivation. I show you the derivation, so you go, oh, okay, I see where it came from, and then just use it. Otherwise, what's the option? I just say, here it is, memorize it, move on, don't ask questions. I don't think that's a good way to do anything mathematically. So my picture, I'm going to do my best here. So what we're doing now, I'm going to take a piece. This is the way I like to say it. I have a sphere. I'm going to take a little coarse section of the sphere. Now, when we have our three-dimensional object, and I said, make a grid on the xy plane, make a grid vertically, and we broke it up into a whole bunch of little rectangular prisms. Right? And then I can talk about the volume of one prism and then do my Riemann sum. Well, the problem with a sphere is I'm not going to get prisms per se. When we did it with the circle and I took the wedge and I split up all the little pieces, remember I had all these little archy pieces and we found the area of each of these. They're kind of rectangular-ish, but not exactly. So I'm going to take a coarse sample of the sphere It's going to be very much like a prism, but it's, it's going to get a little wider as it goes up. So I'm going to do my best to draw that thing. All right? So that core sample is going to kind of look like this. It's kind of what it looks like. I can do circles and spheres. Okay. That's kind of what it looks like. Let me try to make it so. In other words, I kept going. So that's coming from the sphere. I took a little chord. So the question is, what are all the individual pieces? What are they? Well, if I take this and I go straight down, let's see. I drew it for myself so I can make it look like something here. Yeah, that's about right. This translates to there. So that angle right there, we're going to call delta theta k. That's on the xy plane. That's definitely a theta change. Everybody okay with that? We're going to call this piece right here, because I'm coming from the center, that's going to be delta rho sub I. I'm going to write it like this. Okay, so this opening right here is a delta theta. Therefore, what do you suppose that opening right there is? That's going to be a delta phi, and I'll use J. So I've done this independently, and the I's will go with the rhos, and the J's will go with the phis, and the K's will go with the thetas, because they don't. And then what do? We do the triple sum over the I's, over the J's, over the K's, like we did with rectangular. What's the volume of that thing? Oh, the volume of that thing is technically, in a sense, going to be that times that times that. It's kind of prismic. It's not exactly prismic, but if I make it small enough, I can use the prism like we did with the circle. I can kind of think of it as rectangular in that sense. So I remind you off to the side, something we already know, we already did today. If I put those two together, then I get S equals theta over 2 pi times 2 pi r, which means S equals r theta. Oh, that's equal to the radius times the angle. That's a very important result. I know the arc length in the sector is always equal to the r times the theta. And in that case, r would have length units, S would have length units, theta would be in radians, but radians are technically a unitless thing. So that's off to the side. Why am I doing that? Because I need that for these individual pieces. So the three pieces I've just figured out then, this piece right here, that piece right there, is, it's getting kind of muddled. How's that? That's rho I sine theta, I'm sorry, sine phi j delta theta k. Rho sine phi is the radius portion, and then times the angle, right? Because I'm doing basically that. Okay, this piece here, got to give you a little distance. That's rho sub I delta phi j, just that width there, and then of course that length there is just delta phi. That's easy. There's no angles. So what is the volume of this piece? We'll call it the ijk piece. It's going to be the product of these three. So it's going to be rho I sine phi j delta theta k. Again, I'm showing you where it came from. I don't need you to ever reproduce this. Times, let's take that one, rho I delta phi j, and then finally times delta rho I. Big yikes. But if I multiply that out, what I get is so what do? We take the Riemann sum, we take the limit as the norm of the partition, which would now be the largest such prism goes to 0. And what does this end up becoming? What did we do in polar? We had an r dr d theta. I didn't tell you to introduce the r. The r showed up when we did the geometry and we found the area. Now when we convert to spherical, when we change it to spherical, we are going to introduce, in the same way we did the r, we're going to introduce rho squared sine phi. That's what goes along for the ride when I go to spherical. Okay? The derivation is pretty nasty, but that's the additional piece that will go with every problem. Question?
Just right after the sine phi, is that a d or is that phi? Like on the last equation.
Rho squared sine phi d rho d phi d theta. So in other words, when I do my integration, so let's do something very comfortable. I always like starting with something we already know. Let's find the volume of a sphere using this. All right, we're doing the sphere. The sphere is centered at the origin. I have the sphere x squared plus y squared plus z squared equals a squared. I want to find the volume of this particular sphere using spherical coordinates. Now, the way we found this in Calc 1, in case you forgot, is we took a semicircle in the xy plane and then we rotated it around the axis to create a three-dimensional solid, and then we did the slices. You guys remember doing those? And you used the dishwasher or the shell method. You did stuff like that. But that was a special case because you did that in Calc 1. No, I want to do this as actually a triple integral. So what we're going to do is we're going to do the integral. But right off the bat, we're going to do the d rho, d phi, d theta. Now, I am integrating. I have no integrand. My integrand would be a 1. I'm not giving you a density. So Zachary, here's where if I gave you a density, I just throw the density in the integrand. But regardless of density or anything else, this automatically goes in. So I have a rho squared sine phi. That goes in no matter what. But if I don't put anything else in, this will give me the volume. Now all I need to do is figure out the limits of integration, which is fairly simple, because theta clearly is 0 to 2 pi. Phi will be what? 0 to pi. And rho will go from the inner to the outer, so that will be 0 to a. And if you look at this, this actually is a pretty simple integration. There's really nothing about that should give us, too much challenge. Usually the order is rho, phi, theta, because theta is pretty much always going to be constant again. Phi is probably going to be constant. But what you're not going to see is a lot of functions of theta, but you will often see functions of phi. I have a sine phi. That's why you want to do phi probably before you get to the end. And rho will often be a function of something else. Because it's a sphere, I had constant limits, but that's not always the case. Okay? So this order is the prescribed order. You don't have to, it's just that everybody does because it's usually, for pretty much every problem, it's going to be an easier path. So I'm integrating with respect to rho first. So I'm going to get 1/3 rho cubed sine phi from 0 to a d phi d theta. Remember, I'm evaluating rho first. So that's now 1/3 a cubed sine phi d phi d theta. And make, really take the time. Most people do it kind of as a cursive thing. The vertical and the horizontal is important. All of us, myself included, if we're even the slightest bit sloppy, we will misinterpret. We'll look at a rho, or excuse me, a theta and see a phi, or we'll look at a phi and see a theta, because we were not very careful. Okay, so yeah, don't want that mistake. All right, now I'm integrating with respect to phi, so this will be what? Integral of sine phi with respect to phi would be negative cosine. Yeah. So negative a third a cubed cosine phi from 0 to pi d theta. All right, go slow. So I've got negative a third a cubed times cosine of pi minus cosine of 0. All right. What's cosine of pi?
-1.
Yeah, you can't afford a boo-boo there. So I got -2, but I already had a negative. That's a good thing. That means my answer is going to remain positive. So what have I got? 2 times, so I have 2/3 a cubed d theta. A is a constant. So can I simply multiply my integrand by 2 pi? Can I do that? Yeah. So what's my answer then? 4/3 pi a cubed. Right? Crowd rejoices, confetti everywhere. That's the volume of a sphere. Yay! Oh, it means we did it right. But that's actually significantly easier than what you did in Calc 1 or anywhere else, because you had constant limits of integration all throughout the problem. That's kind of nice. Now, the most important shape there is. Well, certainly from this point of view. The most important shape of all. In fact, I'll go back to that picture. It's such a great picture. I want that cone. Well, the volume of a cone, that's a piece of cake. No. With the ice cream on top. You guys understand what I'm saying? It's not a flat top. So I'm taking a portion of this sphere with the curve on top. So literally I have an ice cream cone with the ice cream on top. I want to find that volume. Ooh. Well, now it does matter how I describe that cone. So that cone is z equals square root of x squared plus y squared. That's the top half. What if I wanted both pieces? Does anybody know what it looks like if it's both pieces? No, it's actually just z squared is x squared plus y squared, which would be the plus or minus root. This is top and bottom. This is just the top. A lot of times we get these confused because this z can be positive or negative, can't it? That's why it'd be plus or minus root. So I just want the top half. Now, here's what makes this work. If my coefficients were not 1, if they were not both 1, this is actually way more challenging. It is way more challenging, but because both of my coefficients are 1, this is actually fairly simple. Because now when I look at this in the xz plane, what will I see? This. That's in the xz plane, this will be z equals x, this will be z equals negative x. Both of these lines have 45-degree angles. In the yz plane, what will I see? The same thing, z equals y, z equals negative y. So what are we looking at right now if we close one eye? We're looking at the yz plane. If we're looking at the xz plane, we're still seeing this, aren't we? What you see are two lines with angles of 45 degrees. Why is that an important thing? Because that's where my phi limits are coming from. So if, just so you know, this is a fair question, what if I put coefficients on either or both? Oh, okay, now it's not so easy. Remember, the slope of the line is always equal to the tangent of the angle. This is an absolute. If that's theta, the slope of the line equals the tangent of theta. That's always true. So if the slope is 1, that means theta must be 45 degrees or pi over 4. But what if I put a coefficient on there? Then the slope wouldn't be 1, so my angle would not be pi over 4. When you have coefficients, your limits of integration are no longer things like 0 to pi over 4, the things like 0 to inverse tangent of 2. Right now it's inverse tangent of 1, which is pi over 4. I'm telling you that because that's the absolute, that's the way it is, but we're praying that we never look at that problem. So I'm not going to ask that problem. I'm going to do the one with the 45-degree angles so that we can navigate through. So in this problem here, I want the volume of this cone. Well, see this, when you did polar coordinates way back when in trig, hopefully you looked at one like this. You certainly should have looked at one like this in Calc 2. When theta equals 0, where am I? I'm here. And as theta increases, by the time theta gets to pi over 2, where am I? Here. Now, as theta starts going negative, or I should not say not pi over 2. Theta starts going into the second quadrant, aren't my r's going to be negative? Oh, what happens? That just means you go the opposite direction. So when I start getting thetas over here, it's going to send my r's this way. So pi over 2, now theta equal pi. Which means I just completed my whole circle from 0 to pi, not to 2 pi. In fact, if your shape is not centered at 0, it's never 0 to 2 pi. But what mistake do most people make? They always go 0 to 2 pi. So if I did this integral from 0 to 2 pi, you said, no, I'm going to find the area of the circle, and I'm going to, because I now know this is a circle. By the way, do you know what the area of the circle is? It's a circle of radius 1/2, pi r squared. What should the area of my circle be? Pi over 4. Pi times 1/2 squared. So we all agree we know the answer before we start. Agreed? So I'm going to do the calculus. This is a piece of cake. And what do I get? Oh, but wait a minute. Am I integrating cosine? No. I'm not integrating cosine. Oh, I've erased it. What is our integrand? Doesn't it have to be 1/2 r squared? Right? It's 1/2 r squared? Oh, see, that's a rectangular integral. That's not correct. I've got to integrate 1/2 r squared. Ooh. Oh, that's right. Okay, that's the polar thing. All right, let me erase this. So this is the other thing that can come up. You can't integrate the square of a trig function. You got to use one of the double angle formulas. So we know that cos squared theta is 1/2 of 1 plus cosine of 2 theta. We know that the sine squared of theta is 1/2 1 minus the cosine of 2 theta. These are really important identities that we learned as babies in math that we use actually a lot. So that means I got to do this because I can't integrate this. So this is now going to become 1/4 the integral of what? Of 1 plus the cosine of 2 theta d theta. That integral is easy. This is going to be a 4th theta plus sine of 2 theta, and what's going to go here? 2. Careful, is it a 2 or is it a 1/2? If I differentiate it, it's a 2, so if I integrate it, it's a 1/2. 0 to 2 pi, well that's easy because the sine at 2 pi and the sine of 0, those are both going to be 0, aren't they? So this is easy, so what's my answer? It's just 1/4 times 2 pi, which is pi over 2, right? And now this time you use the shower scene in Psycho, you know, with the big blade. You guys know what I'm talking about. You know, every movie they have the knife and they play the violin in the background. And, oh my God, my world just turned upside down. My geometry formula pi r squared is completely wrong. You told me the answer had to be pi over 4. Why isn't it pi over 4? Because that's the wrong limit of integration. I'm proving it to you using calculus. That was supposed to be a pi, wasn't it? And if that was a pi, then this would have been a pi over 4. Do not make the assumption that your angle is 0 to 2 pi all the time. But if it's centered at 0, a completed shape will always be 0 to 2 pi. That's comforting, and most of the time, not all the time. Most of the time we're centering it at 0. But if you grab any calculus book, there will be a significant number of problems where it's not centered at 0. It's this problem here, and you've got to account for that to say, what does it take for me to complete my shape? Because that's really, really important. And I'm not even talking about what if I said 2 theta. Ooh, we hate those. Those are even gnarlier, right? So, With that said, we can set up this problem fairly easy because we do have circular limits. You don't always have circular limits with polar. There's two reasons you go to polar. One is your limits themselves. Your boundary was circular in nature, then it doesn't matter what your integrand is. You're going to change x's to r cosas, you're going to change y to r sines, and x squared plus y squared you're going to change easily. What if my integrand involves x squared plus y squared in general, or x squared plus y squared to a power, or maybe x squared plus y squared under a root? Then I need to go to polar, because I won't be able to integrate that otherwise. Here's what I mean by that. Again, just strictly polar. I'm asking you to do something of this nature. It doesn't matter what my region looks like. This is not possible to integrate in XY world. There is no trick. Well, can I do a trig sub? That only works for one independent variable. There is no substitution you could do here. Does that make sense? So I would do polar, and then this would just become r. R d r d theta. So now I have a really easy integrand. Now my limits might be hideous and ugly, but my integrand would be easy. What we would prefer is that this be circular in nature to go along with this, which, by the way, more often than not, that is what's happening. That I have a region that is circular in nature and an integrand that would benefit from switching. And then when I do that, I end up getting a really easy problem most of the time. Everybody cool with that? All right, so let's do this problem. What is my mass? It's the triple integral over the volume of my density dV. In the immortal words of George McFly, you are my density. I have to. My daughter's best friends. Every time she came over, her name was Destiny. I always had to tell her, you are my density. You guys know what I'm talking about, right? Involves you Back to the Future. Now what? I got to change this. I'm not going to integrate this in XYZ plane or XYZ space because it would be too terrible. But the Z is not an issue. In fact, Z is going to have constant limits, isn't it? Z is a piece of cake. I'm not even worried about that. So Z is going to go from what to what? 0 to 15, 1 over Z plus 1. But I'm switching it to polar in the XY world, which means I now need an R, dz, dr, d theta. This is what's different. You've not done this, but this doesn't make it hard. I just got to kind of keep track. Now, you'd usually go dr, d theta. Could you go d theta, dr? Yes, but if theta, I would be hard-pressed to come up with a problem where theta wasn't constant limits. But it's really easy to come up with a problem where r is not constant limits. R is generally going from a function of theta to a function of theta. This is why you always go in this order, because the r limits may not be constant, even though the theta are always going to be constant. Does that make sense? If the r limits are not constant, you don't want the r on the outside. Okay, it'd be too difficult to try to rewrite it. So the r, what is my base? Isn't my base x squared plus y squared equals 6 squared? So that is the circle r equals 6. So when I do my little pie-shaped wedges, the r's will go from 0 to 6. And because I'm going all the way around, now, regardless of what my integrand is, I can't get a friendlier integral from this standpoint because all my limits of integration are constant. Had I done this in XY world, I'd have square roots of nasty things all over the place, wouldn't I, for my limits? That would be an extremely difficult problem. This problem here, pretty safe. All right, so let's do this. Antiderivative of that guy looks like the z's on the bottom. Natural log. So that's going to be natural log, absolute value z plus 1 times r from 0 to 15 dr d theta. Okay? When I replace z with 15, I get natural log of 16. When I replace z with a 0, I get natural log of 1. What's natural log of 1? 0. I love natural log of 1 showing up in the problem. So this is just log 16 times r. Log 16 is a coefficient. You can pull it out in front of the integral if you want. Okay, dr d theta. Okay. Now what? Now we integrate with respect to r. So that's 0 to 2 pi times log 16 times 1/2 r squared, where r is going from 0 to 6. Well, that's pretty nice. So I have half of 6 squared minus 0 squared, which would be what? 18. So now I am at 0 to 2 pi of 18 log 16 d theta. 18 log 16 is a constant. I'm integrating a constant over constant limits. I can simply multiply this by 2 pi minus 0, and I'm going to get 36 pi log 16. Pretty horrible looking answer, but wasn't that hard to come up with. Okay, it's a number. We didn't give it units. If we had given it units over here, the density units, and we did give centimeters, but I'd have to give the density some units, and you could tell me what this is. This is a mass unit, okay? So, since it was metric, what are my units most likely going to be? What kind of thing?
Grams.
Probably grams, yeah. Probably not kilograms, probably grams. Okay, don't worry about that, because remember, we're looking for center of mass, so in center of mass, all the units cancel anyway. That's why it's less critical. Okay, now let's do the moments. I got 3 moments. Wait, so let's start with the moment. Let's do the moment to the xy plane first. I think that's the most interesting one, because from a mathematical standpoint, that's the one that's going to be the most work probably. So that's the one that involves the z distance. Okay, so before, I'm going to switch it to polar, that's not a question, but I want to set it up correctly. So I find it useful to set it up in this form first, then switch it, because you don't always know which parts are going to be changed. When we do the other moments, we have to introduce the multiplier of x or y, agreed? Introduce the multiplier of x or y, then change it to polar. Don't try to change it to polar before you do that, bad things can happen. So what is this going to be? It's going to be this integrand times z. And then dv. Now, we're going to go polar. That's not a question. But what does my integrand become? Z over z plus 1 doesn't look entirely friendly. Okay. Now, everybody understands that you can always do things like this mathematically. Okay, and in fact, almost 100% of the time, it's useful to pull things apart. I can get z over z plus 1 by using long division, by using synthetic division, or doing what they started calling back in the 80s, 90s, Brown division. I don't ever actually do long or synthetic. I mean, I do it occasionally. It takes too long. And I don't say this jokingly. Almost every algebraic process you've ever learned in your entire life, no matter how many steps it took, almost all of them can actually be done in 1 step. Almost all of them. The most I've ever found was 2. Most people take a long time to do short processes. Plus 1, minus 1. That's the answer whether you did synthetic or long. I don't ever bother with either one of them just because they take too long and people make mistakes. Add and subtract to your numerator and then pull it apart. That's what I do. I started doing that as a kid and I would teach my teachers that and they're like, I didn't know you could do that. I'm like, well, you're filling up a page and I'm just doing this in a second. You got to get the answer. You just don't want it to take any time. Why is it important? Because I can't integrate that. That cannot be integrated. That can easily be integrated. So I'm going to make this 1 minus 1 over z plus 1. If I put it back over a common denominator, it's easy to see, times r dz dr dθ. Okay? Not pretty, But we just did something like this over here, so I know I can do this fairly simply now. All right, I'm integrating with respect to z, not with respect to r. So with respect to z, that's just going along for the ride, remember. What am I going to get? Z minus ln z plus 1. Actually, you know, I'm going to leave the r on the inside. I don't like the way that looks. Hold on. Let me do it like this. R, there we go. I don't like the limits to be inside the variable, and then dr d theta. All right. When I evaluate this at 15, what am I going to get? We get 15 minus log 16. Then when I evaluate it at 0, I'm going to get 0 minus log 1, which is 0. Oh, okay, so I'm just going to get 15 minus log 16 then. Beautiful. Okay. Now at this point, constant times r, that's not an issue. So how about 15 minus log 16 times 1/2 r squared, where r is being from 0 to 6. Boy, that sounds familiar. We just did that. And that again is going to be 18. So now I've got, if you will, let's say 18 times the integral from 0 to 2 pi of 15 minus log 16 d theta. Beautiful. So now what have I got? Times 2 pi, I'm going to have 36 pi times 15 minus log 16. It is absolutely correct to distribute that. There's no problem. I'm going to leave it like that for now, just it's easier to read for the moment. You with me so far? Is it ugly? Yes. But when I find my z bar, I'm going to take the quotient of these two, and a lot of stuff's going to disappear. Okay. Let me go back to this board over here, because I'm going to run out of room otherwise. Understand that we cannot do this problem without a triple integral because that I have 3 independent variables and I have an integrand. Right, that's the thing. So now let's do the moment to the yz. That's the one that involves the multiplier of x. So that's going to be the triple integral over the volume of what? Of x. Rho is still going to go from 0 to outer edge. And theta is still going to go all the way around. What's going to change? Phi is only going to go from 0 to what? Pi over 4. Before, it was all the way because I wanted the sphere. Now I just want the ice cream cone. You with me on that? So the change in this problem will be that. Okay. What if? What if I wanted both? You can't do that as one integral, you would need 2. Wouldn't they be identical? So if I wanted both, what would you do? Do that and double it. Okay. Then the third question is, what if I want the other stuff? Then I would start at pi over 4 and go to wherever I need to go to. Because I don't want, if I didn't want the cone. So that's a really common problem that we like to do because we can conceptualize. It's not that hard to see, and I got friendly limits, but I still have to do the integration. So I want to find the volume of the ice cream cone. So what I'm going to do, it's now the ice cream cone. It's now the ice cream cone. Now the ice cream cone. So now is when the problem's going to change. Okay, everything after this is now going to be different. So now it's what? Cosine pi over 4 minus cosine of 0. What's the cosine of pi over 4?
Root 2 over 2.
You want to use root 2 over 2? Okay. Huh. It's not as pretty now, is it? That's correct. It just doesn't look as nice as it did before. This is negative. But I already had a negative here, so I probably would rather deal with those two things. So now I have positive a third a cubed times 1 minus root 2 over 2 from 0 to 2 pi. So my answer is now 2 pi times a third a cubed times 1 minus root 2 over 2. This is correct. That's ugly. Can I make that a little bit nicer? I don't think I want to distribute everything and have a sum. I think I still like a product. Maybe take the 2 only and put it in there. What do you think? Then I won't have any quotients. So I think probably that, well, I'll leave the third in front. So how about if I write it like this? I have a third a cubed times 2 minus root 2.
Times pi. Where's the pi?
Did I lose my pi? Ah, thank you. Pi, thank you. Did that work? I think that's probably the cleanest, any version of that's correct. So the what ifs are, what if I ask you for some other portion? So what I often like to do is, if I asked you for the whole cone, you have 0 to pi over 4, but then you pick it up again, 3 pi over 4 to pi. That's correct. But since you know the shapes are congruent, you can just do 1 and double it. That's safer. But what if I now ask you, this is the only other real question you'll ever see. Okay, there's my cones. I want this. Now, the only way I can describe that is you have an orange, and you chord the top and you chord the bottom. And you can almost put your finger through the center. So I say, think of that as a little piece of wood or something, and you've kind of chord both. It's kind of like a bead. It's not a bead exactly, but everybody understand what a bead? You have a hole in the middle. This is a funky hole because it's going like that. But you have a solid object, it could be an orange, and I'm going to core it, and I'm going to core it, kind of like a bead almost. But I want what the orange that remains when I remove the ice cream cone shape from top and bottom. That's the part that remains. How do I set up that problem? Because that's the one that gives us the most fits, I think, conceptually. If I wanted this, well, if that's 0 and that's pi over 4 and that's pi over 2 and that's 3 pi over 4 and that's pi, and I want all of this, lower limit of pi over 4, upper limit of 3 pi over 4. Beautiful. Now here's one that a lot of folks don't realize you can do. There's some great checks in here. You found the cone, you feel good. Now maybe I'm asking you to find the bead, and you find that independently and you feel good. Could you take the 2 cones, add it to the bead, and then what should you get? The whole sphere. Oh, what if I've already found one of the cones? Do I really need to integrate to find this one? Or could I take the sphere and subtract 2 cones? Would that work? As long as the cones are correct. yeah, it's under the assumption that you didn't make a mistake. Would that work? Absolutely it would work. Now, I'll ask a question on an exam. I'll say find the volume. You know, I'll basically ask you for the bead. It's way faster to do the one integral. It's not faster to do the whole sphere, then do an individual cone, then to subtract 2 cones from you. That's not faster. That's more work. It's not wrong. It's just not efficient. It's more efficient to just find it. But what if you were asked more than one question? Do you need to do an integration for each one? No, you probably only need to do one integration and then use that result and the fact that you already know what a sphere is. You're banking on the fact that you know the volume of the sphere when you start this.
If you wanted to have like an actual bead shape with a hole in the middle, would you just make the bounds for the radius where the start of the hole is?
That one is a little bit trickier. That's a great question. So Zachary's question is, I actually have an orange, and I want to take a really fat straw. How's that? And just go right down the middle of the orange. The problem is what you cut out is not a circular cylinder because it's got a curvy roof. Oh, but I can still use cylindrical coordinates, and my z will go from base to roof. Or base to... Does that make sense? And I can subtract that from the whole.
I mean, if you had the code.
But you can't really do that using spherical coordinates. Because the part you're removing would be cylindrical. Now here's what you can always do. We just did the volume of a sphere using spherical coordinates. Could I have done the volume of a sphere using cylindrical? The answer is yes, because my z would go from, curve to curve. It would have been way more complicated and way more work, but absolutely correct, to use cylindrical on the sphere. What you cannot do is use spherical on something that is cylindrical. It doesn't work in reverse. If I had something that was a circular cylinder in nature, spherical won't work. Because none of your limits of integration would be constant. Okay, think about that. My rho would be different at every point on the cylinder that I hit. Does that make sense? And my phi would be constant. So if something makes sense to do using cylindrical, never use spherical. If something makes sense to use spherical, you can probably go either way, but if it makes sense to do spherical, do spherical. And how do you know? That one's less about the integrand and more about the region. If I'm integrating over a sphere, way simpler to use spherical. Now, I'm going to change one more thing. I'm going back to my original sphere. And I want you to find the mass with density. I'm going to give you a density function, and I want you to find the mass of the sphere. Now, keep it really simple. Anybody ever use a medicine ball? You know what a medicine ball is. Think of a basketball and filled with sand, but partially filled with sand. Or maybe filled with all sorts of stuff, whatever you found in the backyard. So even the particles it's filled with are not consistent. They're not uniform density. So I have a sphere. Is it fair to ask the mass of that sphere? Sure. Is it fair to ask the center of mass of that sphere? It doesn't necessarily have to be all the way full, does it? Or it's filled with different substances, or you filled it with stuff and stuff settled at the bottom, meaning the center of mass may not be located in the center of the sphere. I'd have to calculate. It'd be kind of a pain, but I could do that. How do I do that problem? Right, like that. You have your sphere, and you insert your density as part of the integrand multiplied by the rho squared sine phi. So most of the time when you're doing spherical coordinates, most of the time in reality you're not finding a volume, you're probably finding a mass. Okay, so again, take a spherical solid object that has variable density and ask for the mass. Now, would center of mass still work the same? Yes. But now when I multiply by the x, the y, and the z, now I have to use the rho squared sine phi cos theta, rho squared sine phi sine theta. Yeah, I have to use those. That's not a question I'm generally going to ask. That problem is just too long. You could all do it. But it is a really long problem now because of how many things you have to do within the problem. So understand that problem is a fair question. You're probably not going to do that in a math class in the future. Yay! You probably will do that in a physics class in the future. Boo! Right? Because that is a simple physics application, finding a center of mass of a three-dimensional solid. Why would I ever need to do that? Well, yesterday's lecture? You're designing things? Yeah. Now, are the things you're designing necessarily spherical? Do you think that's a common shape in design? Or I think rectangular is probably more common in design. Probably the rectangle is a little more common, but I still want to be able to do the spherical thing in nature. Okay, let's go ahead and stop the recording. Times 1 over z plus 1. Yes, it is totally correct to make that into one quotient, but because I'm going to be converting to polar, it might be easier to keep them separate. All right, so when I do this, all my limits are staying the same. I'm not messing with those. But now I need to change the x to what? R cosine theta times 1 over z plus 1 times r dz dr d theta. Ooh, that means I'm going to have an r squared now. So let me take this. I'm just going to go like that. Now it's r squared cos theta times 1 over z plus 1. I'm going to be lazy. I don't want to rewrite the whole thing. All right. Well, I'm still integrating with z first, so I'm still going to have the natural log. So I have r squared cos theta ln z plus 1 evaluated from 0 to 15. This is starting to feel, you know, like we've done this before. So I'm going to have just a log 16. So I have, I'll put it in front. I've got a log 16 times r squared cos theta dr d theta. Beautiful. So now when I move up to here, I'm going to have 0 to pi, 2 pi, 0 to 6. Now I'm integrating the r, so I'm going to have log 16 times 1/3 r cubed cos theta, where r is ranging from 0 to 6. So now I have 6 cubed over 3.
You left the RDO.
Did I lose something?
An extra integral.
Text something.
That middle integral on top shouldn't be there. This side.
Oh, thank you. I already, yes, we just did that. Now I have r cubed over 3, which would be what? Yeah, it's something, yeah, good, all right. 72 log 16 cos theta d theta. So now I'm integrating positive cosine of theta, so my antiderivative will be what? I can't multiply by the limits because I don't have a constant integrator. Positive sine theta, good. All right, from 0 to 2 pi. Wait a minute, if I evaluate sine from 0 to 2 pi, it's 0, isn't it? In fact, it's 0 at both ends. Huh, go figure. You got 0. That is just crazy. That's out of control. Okay, let's now do, I had an orange pen, but I don't know what I did with it. I now want to do, I'm going to do it in blue because I'm going to be really lazy right now. Let's now do xz. What changes? That's a y. So what changes? That's a sine theta. Sine theta. Sine theta. Do you agree everything else is the same? Sine theta. Sine theta. What goes here now? Negative cos theta. Evaluated from 0 to 2 pi. And that is also 0, isn't it? Did we make a mistake? I mean, we got what we got. Let's go over here. X must be, Y must be, Z must be. This isn't questioned, but this is 0. This is 0, and this one is something wicked, I think. I'm going to go ahead and distribute this for one simple reason, so I can cancel easier. So that's going to be 540 pi minus 36 pi log 16 over, I believe, 36 pi log 16. Do you agree with that? The reason I'm going to cancel, or I mean do that, because now I can do that. Do I get lots of canceling here? Well, I get tons of canceling. Or, you know, it might have been easier just to cancel the 36 pi's at the beginning. But my final answer is going to be, looks like 15. Sorry, 15, what's my denominator? 15 over log 16 minus 1. Because that's going to be a 1. That's a weird number. Somebody put that on your calculator for me, please. Because I want the answer to make sense to us. I want us to agree. Give me a decimal approximation of that.
4.41.
You're saying it's about 4.41? But my x and y are 0. How is that possible? Well, didn't we put the z-axis right down the middle of the can? And what do we talk about from a gravity standpoint? Things move sideways, they do not change density sideways. They only can change density vertically, because density, therefore, in other words, gravity affects density, doesn't it? That's why it's always more dense at the bottom than the top. When you buy the orange juice, what do you do first? You shake it up, because what did all the pulp do? Went to the bottom. That's gravity. It's always more dense at the bottom, so you shake it up. So my cranberries are more dense at the bottom, but they do not change density going sideways. That's why when I have the z-axis running right down the middle of the can, it makes sense that the center of mass is on the z-axis, because the shape is symmetric. We did something like this yesterday, didn't we? We made a similar argument. So absolutely, I know that the center of gravity is on the z-axis. Now, the z-coordinate was roughly 4.4, and it's 15 units tall. That's way below the middle. Why? Because it's way more dense at the bottom. We would have expected it to be below 7.5, wouldn't we? Because 7.5 would be the middle. So does the answer make sense to us? Hopefully it does. Hopefully it should make sense. Yeah,
So
Katrina?
the answer is the z coordinate where it's the mass is centered?
So this is the answer. Because the question was, what's the center of mass? So that's the answer.
Okay.
But I wanted to justify why is x and y 0? Again, because we centered it on the z-axis. And by the way, that is the wise move, because it made the algebra of our calculus way simpler. We would have set it up correctly, but imagine if your circles were not centered at the origin, how complicated that would be, and then my limits of integration, everything would have been trickier, unnecessarily trickier. Okay? So here's a simple example of using polar. Now, in a moment, I'm going to show you one of the most important derivations in the history of mathematics. In fact, it is the single most important result in the history of statistics. Is what all of statistics is based on a certain result that you will probably be exposed to in a differential equations class, because it's in every book. But the way of evaluating it isn't, because the authors of the textbook don't actually know how to do the problem. They just know the result. That's not uncommon, by the way. It's not evil. It's not evil for somebody to know the answer without being able to show you. When you were in elementary and junior high and stuff, and they said the area of a circle is pi r squared, you were okay with that, weren't you? Could they show you that? No, that actually requires Calc 2. You can't even do that in Calc 1. That actually can't be derived till Calc 2. You're able to do the surface area and volume of a sphere, but not until calculus. But you had no problem with the formula. You had no problem with 4/3 pi r cubed growing up, did you? You accepted it. You never asked somebody to prove it. You knew it was the truth, but you actually couldn't show it until you got to calculus. There are a lot of results that we can't actually show until later, but we still accept them when we understand them. I'm pretty sure most of you, when you leave here and you get into your car, are not going to say, okay, hold on, explain the combustion engine to me first. I'm not turning that key until I understand completely how it works, right? And then with your cell phone, tell me how all of this stuff works. I'm pretty sure you're accepting, right? When you turn on your computer, you don't have to know all the language and stuff. You're okay with that. I have fun with that, because you don't have to know the inner workings of everything. But there are certain things you should know where they came from. Otherwise, you're accepting results that you can understand without any confirmation. And I have used textbooks. Swakowski's a perfect example, where there are errors, where he gives you formulas that are not correct, and there's no derivation. So you can't even question where he got from. Except they're just not correct. Yeah. Well, there's a lot of calculus books with incorrect information, and no one checks it. So I'm going to go through a very simple problem for you right now. I'm going to do the following, okay? I want to do the integral from a to b, c to d of, I'm going to keep it simple, of f prime of x, g prime of y, dy dx. My integrand is a product of a function of x and a function of y. If it helps you, maybe it's x squared times y cubed. But what it isn't is x squared plus y cubed. I have an integrand where my functions are connected through, it could be a quotient also, because I could be 1 over x squared. But I have a function of x times a function of y. They're completely separate functions, and I'm integrating over constant limits of integration, which means in the xy plane, this is very, very important that we can interpret this. This is exactly what the region in the xy plane is. And the reason I'm pointing this out is because my region is a rectangle, I could have easily integrated in either order, couldn't I? Is everybody okay with that? That would have been no problem integrating in either order. So let's do this. So I'm going to do y first. I'm doing this to show you a formula that is not in any textbook. But it's a handy shortcut that you don't get to use very often, but it's really obvious. When my integrand is a constant, you don't have to do the last integral. You can multiply it by the length. You now know this. That's a nice shortcut, isn't it? It's not a huge time saver, but it's a small time saver. You know that now. You don't even question it. So let's do this. So I'm integrating with respect to y first. So that would be g of y from c to d dx. When I do that integration, I'm going to get a, b, g of d minus g of c, correct? Oops, minus. Okay. Now I got to do this integration. This is a constant. So this will now be f of x times the constant and I'm evaluating this from a to b. So this will be, in the end, f of b minus f of a times g of d minus g of c. Okay, is everybody okay with that answer? It's kind of boring, but that's my answer. First question is, I want to switch the order of the integration. Can I do that? Yeah. If I had done c to d, a to b, f prime of x dx, excuse me, f prime of x, g prime of y, dx dy, we would have gotten the exact same answer. Do you all agree? Because you can, I don't need to go through that. You can all see that. That's pretty simple. But that's not the point. I mentioned this before. I said you can always switch the order without doing anything if all of your limits are constant. Because if all your limits are constant, then it means your region is a rectangle. X and y are not functions of each other. They're each constant. So reversing the order doesn't make any difference. But that's not the end result. Now I want you to do something completely different. I want you to do the following integration. I want you to do these single integrals. This is my point. What I just showed you, yeah, that's probably in most books, that you can simply switch them without doing any work when they're all constants. Because again, you got that picture over there. Well, let's see, this is going to be f of x from a to b, which is f of b minus f of a. Okay, that's nice, I know that. This is g of y from c to d, which is what? G of d minus g of c. Okay, so what's the point? Here's the point. I'll write it over here, because it's kind of important. This is a hugely important rule, but it isn't used very often because you won't run into this situation very often. So let me start it again. I started with an integrand that it was the product of a function of x and a function of y. The order wasn't important because my limits of integration were constant. Here's what's important. You cannot do this in general. You can do this in this case only. The double integral equaled the product of two single integrals. That is not a rule in calculus. Please do not do that in general. If I give you a double integral, you can't just pull it apart and make it two single integrals. But you can if all of my limits are constants and my functions are related as a product or quotient, because I can write that either way. Does that make sense? Okay, so if I gave you the following question, I am going from -1 to 3 and 5 to 8 of x squared y cubed dy dx. What I'm saying is, I can now write, I can do this. This is when I can do this. You can't do this in general, you can do this in this case. You with me? By the way, do you think that could be a useful shortcut? Yes, but also think of it another way. This was a pretty darn simple integration anyway, wasn't it? So pulling it apart is correct, but it may not actually be a time saver. That's my point. But that's kind of where we're going here. from a different point of view. Now, how many have had statistics? Okay, you understand what the normal curve is. All of statistics starts with something called the normal distribution. Now, I don't need you to know statistics, but I do want you to understand there is something going on here. All right? I have a function. Okay? I start with this function. Looks like this. The x-axis is an asymptote. This is defined from negative infinity to positive infinity. Okay? But it turns out the area under this curve is actually finite. The normal distribution starts with this. How many have heard the term the bell-shaped curve? This is the only bell-shaped curve. You can make a curve that looks like this, but the bell-shaped curve is very specifically this and this only. There's no other bell-shaped curve. Doesn't matter if it looks kind of like that. That term bell-shaped comes from this. So here's what we do in statistics. I'm going to make the claim, I'm going to prove it in a moment, but I'm going to make the claim that this area is finite. So if I can calculate whatever this area is, let's say the area, I'm going to make it really simple. Let's say the area equals A. Then what I want to do is do this. You guys know what a unit vector is. You take a vector, find its length, and then multiply the vector by the reciprocal of the length, and now you made the vector of length 1. What did I just do to the area under the curve?
Make it 1.
I just made the area under the curve equal to 1. Because in actuality, when you're calculating probabilities, there's two types of situations. There's discrete probabilities, there are continuous probabilities. In calculus, we only deal with continuous things. So I said, you're going to flip a coin 10 times. What's the probability you get at least 5 tails? That's 5 or 6 or 7 or 8 or 9 or 10. I understand that. I'm going to throw a ball. What's the probability I threw it, between 10 and 20 feet? Does that mean 10 or 11 or 12? No. Aren't there an infinite number of measurements between 10 and 20? That's now a continuous measurement. I can't calculate it the same as I did like a coin flip. That can only be calculated by integration. That's gnarly. Oh, so if I have something that's continuous, what if I said, this is what you do in stats. What's the probability of an outcome between here and here? The probability of that outcome is equal to that area. If I make the area under the curve equal to 1, and in all contexts, total probability has to equal 1. Probability cannot exceed 1, it can't be negative. If I take all possible, for any experiment, all possible outcomes, the probability is 1. So what we do in statistics is we say the area is equal to the probability. So those of you who've had stats, you looked up these values in the normal curve or you looked them up on your computer, great. You didn't calculate them. The computer generated the calculations because it's such a complicated calculation. So what you just did was you integrated this from A to B. Big yikes. Well, no, the computer integrated it and then it gave you answers. Does that sound familiar for those in stats? You looked them up, you didn't do the calculation. It's way beyond what you can do. So the question is, how the heck do we find that area? I taught stats for many years. I went back to do the master's program at San Diego State in the early 2000s in statistics. And I think it was my second year in the highest level of the stats classes, the main function. The instructor derived what I'm about to do and I went, oh my God, that is so cool. Now I know it. I'd been teaching stats for 20 years at that point, and I had no idea where it came from. I've talked to many, many mathematicians and PhDs. They had absolutely no idea where it came from. I learned the most important integration, by the way, in all of differential equations also. This result is the most important for diffie-q as well, because we derive a lot of things from this. The gamma function and all sorts of other things come from this integration. Yet, I learned it in a stats class, not in a math class, because it's so obscure, but we now know, as of right now, how to do this, believe it or not. And I'm going to show you. I do this in every Calc 3 class. I'll do it again in diffie-q. I would like you, this is not that complicated of a problem. Wink, wink, nudge, nudge. All right, I want you to evaluate this improper integral, because it's infinities. Oh, and by the way, my integrand can't be integrated. There is no antiderivative of that integrand, period. So I'm giving you a nice challenge problem. I'm giving you an integrand that can't be integrated with infinite limits of integration. You ready for that? Are you ready to change your majors now and say, I think I'll go into something else? Well, question. Here's my question. This, I'm going to call this A. That was our area. True or false? True or false? True?
True.
Does it matter what symbol I'm using for my variable? Just as long as they're the same. Okay, well that's not very complicated, but why would I do such a crazy wild thing? Well, let's see. What if I just for the heck of it, just for fun, because that is our primary goal today, you know, fun. You guys know the fun song, right? Which version are you going to sing though? Everybody knows there's two versions of the fun song. What's the wrong version, Zachary? Do you know? Plankton's version. Yeah, you guys know Plankton's? We're not going to do Plankton's version. We're going to do SpongeBob's version. Yeah, I have kids. I know the fun song. Yeah, at least once a week we hear the fun song in my house. And it is fun. I want to multiply these two together. Just for the heck of it, because it's fun. But that's not the area anymore. What is this?
2 times the area.
Nice.
Do we all agree that's the square of the area? Well, okay. Great. I'm going really far in life. Constant limits of integration. Yeah, they're infinite, but they are constant. Function purely of x, function purely of y. I pulled them apart. Can I put them together? Absolutely. I can now make this into a double integral. This is absolute. There is no exception to this statement mathematically, because I have constant limits of integration, and that's kind of the key here. So I can say, okay, now I really have a crazy problem. By the way, does it matter if I do dy dx or dx dy? Is that going to make any difference whatsoever? No. Okay. You just took an impossible problem, and technically would this be impossible squared? Okay, but you know, I am multiplying two exponential functions there. Do you agree? I will deal with the infinite limits of integration in a moment. But can I put these two together? Can I make that e to the something? What if I factor out the -1/2? Then what would I have? Oh, okay. Huh. Any ideas coming to mind? What do you think, Allie? What if we went polar? You know what they say, once you go polar, you never go back. I think that's what they say. What if we went polar? Okay, just for the heck of it. Remember, I started with an integral that had no antiderivative. So let's see what going polar produces. I will deal with those infinities in a moment. What will this then be? E to the -1/2 r squared r dr d theta. Ooh, guess what? That's an easy integral. That's a simple use of. Now, I have to deal with these guys. They're not technically infinite anymore. Now, the r, here's a kind of a weird thing. Do you agree, regardless of what x, if I said go forever in the x direction, go forever in the y direction, I've just covered the whole xy plane. Do you agree? It's infinite in every direction. So what is the shape of my thing that's infinite in every direction? It's obviously a rectangle, isn't it? Or could it be a circle that's infinite in every direction? Would I know the difference? If I said, take a circle and make the radius infinite. Take a rectangle and make the lengths of the sides infinite. Is there going to be any difference? It's still infinite in every direction. Does that make sense? So what I have basically is a circle of infinite radius. But not infinite angle. What's my angle? 0 to 2 pi. I have a circle of, oh, by the way, what's my radius? Not negative infinity to infinity, 0 to infinity. I just changed it to polar.
How is it 0 to 2 pi?
Because if I took the whole xy plane and I said I have an infinite circle, my circle is still 0 to 2 pi. It's my radius that's infinite.
Oh, okay. I was thinking about the bell curves.
Remember, what we did was, in case you're wondering, that's the bell-shaped curve. Now that you think about it, I just rotated the bell-shaped curve in a sense. So my bell-shaped curve that went forever in this direction has now been rotated. So now it looks like a, I never thought of this before. It looks like an infinite Hershey's kiss. Is that a good analogy? It's an infinite Hershey's kiss. Circular at the base, but because it covers the whole xy plane, it doesn't matter if it's circular versus rectangular, it's infinite. This is now what I've come down to. Now, you guys know you can't do infinite, so I need to do a limit. I need to do a limit, but that's actually easy. That's the easiest part of the problem. I want the limit as t goes to infinity of 0 to 2 pi, 0 to t. E to the negative 1/2 r squared r dr d theta. Now, this guy here is not that bad. I just need to do a simple u substitution. Let's do that off to the side. I'm not a big fan of doing u substitutions and changing things in the middle of a double integral. I have other things, and plus I already have a limit on the outside. Yep. So off to the side. I want to do this. Wouldn't I let u be negative 1/2 r squared, and then what's my du?
Negative r.
Negative r dr. You know, I actually, oh, finally. This is the pen for introducing constants. So what do I need? I just need a negative sign. That's all I need. Now what do I got? Negative e to the u du, that's negative e to the u plus c, that's negative e to the negative 1/2 r squared. Now I'm coming back to this. So now I've got 0 to 2 pi. The antiderivative of this is simply negative this. From 0 to t and then d theta. I don't know about you, but I'm starting to think this is doable. Okay? E, I got negative e to the negative 1/2 t squared plus e to the 0. What's e to the 0?
1.
As t goes to infinity, that's a negative exponent. What's happening as t goes to infinity?
Approach 0.
It's approaching 0 very rapidly, in fact. Because it's a, yeah, by the way, if the exponent were positive, this would be approaching infinity with it. But it's approaching 0 because the exponent's negative. So that means, a lot of times in calc we do things like this, just to remind us. That term is approaching 0. That's where you use an arrow. You never use an arrow as an equal. You use an arrow as an approaches. Well, is that important? Yeah, because I'm done with the limit now. I now have, this is equal to the integral from 0 to 2 pi of what?
1.
Oh my gosh. All of that came down to this. And what's this? Who knew? The unintegrable thing with infinite limits, almost. What did we just calculate?
The squares.
We calculated a squared, didn't we? So what does my a equal?
Square root of 2 pi.
Now, if you look in any stats book, it will tell you the normal curve is 1 over the square root of 2 pi times e to the thing. And most students will ask me, where the heck does the, they don't ask me where the exponent comes from, they say, where does the square root of 2 pi come from? Wouldn't you say that's weird? Because we just calculated the area under the normal curve is the square root of 2 pi. Therefore, if I put 1 over the square root of 2 pi, I now have an area of 1. Turns out this result is astronomically huge. The normal curve is where everything starts in statistics. I don't need you to know statistics. I need you to know there was actually a way to integrate that knowing only what you know based on today. In other words, adding polar to your repertoire in 3D, which is what we just did. We just did cylindrical coordinates in a sense, in polar. Kind of cool, huh? But this now explains a result that a lot of you will be asked to understand later on without knowing where it came from. And, you know, I would be surprised if your instructor knew. I did not know from my math experience in teaching a math class. I actually saw this in a graduate stats course of all places. But that instructor, he was a theoretician and stuff, so he liked theory and deriving things. And I actually was beaming and I danced on my desk probably for a couple minutes, and you know, I was pretty excited. All right, that's cylindrical. Now we're going to go to its evil twin. Well, adopted evil twin, I guess. Okay, this was Thor. We're now going to look at Loki. How's that? We're going to do something called spherical coordinates, which are a lot less fun. Spherical coordinates, okay, go back to polar for a moment, 2 dimensions. When my regions are circular in nature, polar just makes everything so much easier because I get integrands that I may or may not be able to work with easily, but now there are and thetas rather than horrible functions of x and y. And my limits of integration more often than not are constant in r and theta. Life is good. Now, all we did was extended that into 3D by thinking circular cylinder. But if I have something that is spherical in nature, cylindrical coordinates are probably not going to be very effective. It's not that I can't do them, but they're probably going to be a lot less useful. Okay? So instead, I made myself pictures to remind myself which part. I am going to show you how to convert things into spherical coordinates. Okay? So, all right, I have a point x, y, z. Okay? We already know the polar stuff. Actually, I'm going to need that put down just a little bit. Now, this point is the point x, y, z, so this will be 0, 0, z, because I'm projecting it that way. Now what I want to do is project it onto the xy plane, so now it's x comma y comma 0. Okay? And right here, that would be a right angle. Because that thing I just created was a rectangle right there. Okay? Everybody okay with that? This is the xy plane. I mean, lest we forget. So that angle there, that's theta. Okay? I have a point right here in 3 space. I first went back to the z-axis straight across. So here's x, y, z, there's 0, 0, z, okay? I projected it straight down onto the xy plane, so that's now x, y, 0. Now I want to go back to the origin, okay? What is this distance? On day 1, remember when we talked about sphere and the...
Did you already put the z-axis up or?
Oh, thank you, yeah. That's just crazy math. Okay. Remember on the first day of class when we talked about spheres? What did we call the radius of the sphere? Do you remember? Well, we didn't use r. We used rho. You never in any context use r. Oh my gosh, that would mess things up. On my picture, by the way, that is r. That is r. Right? Going from the origin on the xy plane to the point on the xy plane, that's r. That is rho. Oh, rho would be the distance from a point in 3D to the origin, because if I had a sphere going through that point, rho would be the radius of the sphere. We use rho as the 3-dimensional distance always. Now, when I projected this point onto the plane, the 2-dimensional distance, that is what we call r. That's what we called r in calculus and pre-calculus and trig.
What if you're doing a density problem that has a 3-dimensional radius?
Well, hold that thought. We're going to do that. Yeah, once we establish this, that won't be an issue. Because you'll know how to set up the problem, and that will just be part of your integrand. Because if you have density, density is always part of the integrand. It's never part of the limits or the boundaries. So, okay, everybody cool with what I got so far? Now, this angle here. All right, I need my visual aids here. Okay, I'm going from the origin out to this point here. When I project down, that angle made with the x-axis, we know that's theta. That's by definition theta. But I now have an angle from here, this three-dimensional thing. I have an angle made with the z-axis. That has absolutely nothing to do with theta. That one is called phi. Now this is where it gets a little bit dicey. Theta and phi will always coexist in every problem at the exact same time. And if you're not careful, I mean, I will be quite honest. You know, when I'm lazy and I'm making my, people get lazy when there's only one angle. But now that there are going to be two angles, you have to go really slowly. And I always laugh because never in my life have I ever seen a mathematician or anybody doing math make a zero that didn't look like a zero. But I have students who make all of their zeros look like a different shape. And it makes me laugh because this is one of the most commonly used symbols in mathematics. It always means theta, it never means zero. This always means phi, it never means anything else. And some of you will use this and this in the same problem at the same time when you've already given me one of these. I've never quite understood why you would change a zero because you never use an O in mathematics. So it's actually impossible to ever misinterpret a zero. But these are symbols that you use all of the time in calculus, and they never mean zero. They're angles. They always represent angles. So I would strongly suggest never make a zero not look like a zero anymore. I don't say that jokingly. I have no idea why anybody would. And some people tell me, well, that's the way we did it in the military. No, the reason they did that in the military was back in the 80s, computers made zeros look like this, and they made O's look like this. So what they did was they did a diagonal slash, a diagonal slash on the computer. So when you accidentally typed the wrong key, you could tell because it looked different. That's the only reason that was ever done. And I have everybody still tell me, well, I learned in the military to put slash. No, you didn't. That was only computer code, and they stopped doing that in the 80s. Literally, they stopped doing that in the 80s, but people still do that. Don't do that. Don't make zeros look like something that's not a zero because that symbol means something. So phi is the angle made between the line segment to your point and the z-axis. So there are two different angles. Now here's a really important thing. Theta is on the floor. Tell me about theta. It can range
0 to 2 pi.
Yeah, I'm gonna hit my head. So 0 to 2 pi. Phi is the angle made with the z-axis. Now phi is pi over 2. Now phi is pi. Phi is now done. Phi is the angle made with the z-axis. Phi can only range from 0 to pi. Phi can't range. You say, well, then wait a minute, what about the other side? I want you to think of it like this. Pick a phi, okay. Now, theta makes me go all the way around. Pick a different phi. Theta makes me go all the way around. Pick a different phi. Theta makes me go all the way around. If I keep going, will I eventually carve out a sphere using this sort of reasoning? Yeah, but if I go all the way around, I'll get a second sphere. Okay, so the limits, or the boundaries I should say, we know theta potentially could go from 0 to 2 pi. Phi can only go from 0 to pi. In fact, on the xy plane, phi is pi over 2. So I've already covered. So in the hemisphere, phi would be pi over 2. Okay? So with that said, what we want to do is establish a relationship between x, y, z, rho, phi, and theta. Rho, phi, and theta are the three variables you're going to use in spherical coordinates. Okay? Now, I say it's a little more confusing because this requires what's called spatial. S-P-A-T-I-A-L. Spatial, not outer space. Spatial reasoning and thinking. And again, I'm giving you a picture of a three-dimensional rendering. So let's start with the easy thing. X squared plus y squared plus z squared is equal to rho squared. Again, my three-dimensional Pythagorean theorem. Okay? We've seen this one before. But That means that's true, isn't it? Because x squared plus y squared already equal rho squared. Now, I know that x equals r cos theta. I know that y equals r sine theta. I know that from polar. So now that we're going into 3D, I got to figure out how to make that work. So now look at the picture for a moment. Think SOHCAHTOA. Okay? Oh, by the way, if that's R, then that's also R, isn't it? Think SOHCAHTOA. Now, there's a right angle there. Remember, I'm drawing you an image, so that's coming straight out of the board. There's a right angle, so in this triangle, that would be my hypotenuse. Think SOHCAHTOA. What's the relationship between R, phi, and rho? So R equals rho sine phi. Does that make sense? Okay. R equals rho sine phi. What does Z equal? Because that's Z. So that'd be rho cos phi. Again, that's just straight up SOHCAHTOA. So again, in my picture, I'm coming out and then going straight down, and there's a rectangle there formed. Okay? So far, so good? I want to use this to be able to rewrite this. Oh, if R equals rho sine phi, then replace that R and that R, and then what does this become? I'll just write it again. X equals rho sine phi cos theta, and then Y would equal rho